All right, good afternoon, everyone. Welcome to today's webinar. My name is Laurel Kays. I'm based here out of NC State University Extension Forestry, and I help coordinate outreach for the Southern Fire Exchange. Also on the line today is David Godwin, who's our director, and Marianelle Armstrong, who is our other outreach coordinator based out of the University of Florida via Tall Timbers Research Station in Tallahassee. Today, I'm really excited about our presentation from Dr. Matt Jolly, research ecologist with the U.S. Forest Service Rocky Mountain Research Station with the Missoula Fire Lab. Today, he's going to be providing an overview of the U.S. National Fire Danger Rating System version 4.0, including lessons learned from implementation here in the Southeast. Now it's my pleasure to introduce our speaker today. Dr. Matt Jolly is a research ecologist with the U.S. Forest Service Rocky Mountain Research Station, Missoula Fire Sciences Laboratory. Dr. Jolly's research is focused on three main areas: physiological controls of flammability in living plants, modeling wildland fire potential and behavior, and science delivery of spatial wildland fire potential information. So welcome, Matt, and just 1 minute as we trade out our presentations.
Just want to say thanks for the opportunity to join you today. We have been working on the fire danger rating system actually for a very long time now, starting in about 2005, exploring the ins and outs of the system that we had. It is a fundamental system to the way that that we do business around the country, both for state and federal firefighting agencies, as a decision support system, but it had received very little attention in research for a good almost 30 years before we even started looking into it. And I just want to share today a little bit about this, the ins and outs of the new version 4 fire danger rating system, and then a couple of observations from the calibration of this system for the southeastern states, and then kind of close out with a little bit of featuring some of the things that we're working on that are bits and pieces of this bigger fire danger picture. So in wildland fire, we have decision support systems that allow us to guide decision making at different stages of fire management. So before the seasons even start, when we're doing hazardous fuels treatment or some other pre-season planning, we have systems that allow us to look at where fires will happen. So how we invest in firefighting resources, interagency fuels treatment decision support systems that allow us to locate and perform fuels treatments ahead of time to reduce risk. But what we're going to focus on primarily are these middle two pieces. So our work in preparedness and wildfire response, specifically how that's supported by the fire danger rating system. And also share a little bit about this Wildfire Safe application that we're developing to help make accessing fire danger information a little bit easier. So as we're going along, the fire danger uses are vary across the country, but they really kind of group into two categories. So the things that we do before a fire actually starts, and then the things that we do when that fire starts to guide how we respond to it. So immediately during initial attack specifically. So under preparedness, we use fire danger for staffing to decide how many people we need to keep on. Do we need to work weekends? Do we need to work past a certain time of the day? Seasonally, do we need to bring on additional resources during periods of high severity? Pre-positioning, so allowing us to use fire danger information to pre-position aircraft or crews in specific places of high potential when we know we may have new ignitions that could spread rapidly. But we also use it as a communication tool for prevention and community awareness. So indicating where Smokey the Bear's arm points to tell the public what the conditions are so they can be safer, instituting open burning restrictions, and really tying all that back together to just community awareness in general. But internally, for firefighting agencies, we generally use fire danger for dispatch levels. So how many resources and what types of resources do we send when a fire starts? but also for situational awareness and risk management for our further responders, in a way to develop appropriate strategies that help keep firefighters and communities safe. Historically, we've talked about fire danger in terms of the year that the systems were released. And the very first thing that we learned through this process is that it takes a long time to implement something new. And we kept talking about NFDRS 2016, NFDRS 2016, until we realized that these processes of changing a model, changing all the subordinate plans and rolling it out to the field is very challenging. So we move towards a versioning system so that we can communicate more clearly what is contained in a specific version, so that it's easier to talk about and easier to move forward when we make changes in the future. The first fire danger rating system was in 1972. So before that, there were fire danger rating systems used throughout the country, but they were all different. They all had different inputs. They all had different algorithms, and they merged all those into this 72 system, and to make the first national system, and then modified it in 78 and 88 to basically account for some of the things that we're still struggling with a little bit, with things like the live fuel dynamics and different fuel characterizations across landscapes. So, but in 2016, after a lot of deliberation, we launched version 4, started rolling it out into all the tools, so Fire Family Plus and WIMS, and we're finalizing that finally this year to get everyone on board. So, but really, one of the things that this process has been is the process of tidying up. So during our furlough a few years ago, our family embarked on the Sparking of Joy, which is it's from a book called The Life-Changing Magic of Tidying Up. But I was always struck by how the parallels between this process of a person who tells you how to clean up your life paralleled the way that we started about improving the fire danger rating system. So we went through all the components of NFDRS. We looked for the components that spark joy, and whatever components we could let go of, we let go of them, so that we could keep all of the fundamental pieces that work well. We could strip out the things that weren't adding value and move forward with a new system. So we started that in 2006, but it took us almost 10 years to pick through all the pieces. And then now in 2022, we're implementing the changes. This is the final year for all the units to move over. So what a fire danger rating system does is basically take weather, combine it together with information about fuels and some indicators of terrain to compute a series of live and dead fuel moistures. So those live and dead fuel moistures are really the fundamental pieces of the fire danger rating system. So they're why we focus so much on them in these changes, because the way the model was developed originally, you can go in and essentially pull out a live fuel calculation or a dead fuel calculation, plug in a new calculator or algorithm for that fuel class, and change the underlying dynamics of the model. So that's essentially what we did. We started out by pulling out all of the dead and live fuel moisture models that were in there and replacing them with new ones. The fire danger indices themselves, however, stay exactly the same. So the same indices that were created before, the energy release component, burning index, all are identical. But really what we've been focusing on as part of this rollout too is how do we take fire danger information, make it categorical, and tie it to decision making. And we'll try to weave that in as we go along today, because fire danger is a decision support system. The fire danger rating system supports preparedness and response decision making. Decision support systems have basically 5 major components. So they have the modeling system itself, so the algorithms of NFDRS, how we take all of that weather information, condense it down to an index that can be used to make a decision. But all the other pieces are important too. And we've learned over this process that we have to focus on each and every one of them for a rollout of a new system to be really effective. So we know that a knowledge engine means tells us how we apply a specific modeling system or an index in decision making. So those are our fire danger operating plans or our fire danger application documents. Each agency has some control over how they actually implement the system, but it's very well established in policy and requirements to have a way to do that. The other underpinning pieces of it, which are often forgotten, are the data management systems that support them. So how do we, where does the data come from? How do we store it? How do we analyze, calculate fire danger against it, analyze the relationship between fire danger and fire activity, and then some sort of user interface. So our systems that we use for these two pieces, the data management system and the user interface, are the weather information management system, which is a real-time system that gathers RAWS data, remote automated weather station data all over the country, brings it into a central calculator, computes all of these new indices, and then publishes them for use by both federal and state agencies. The same with Fire Family Plus. Fire Family Plus is the way that we do the historical analysis, but the calculators are the same. So one of the things that we did through this process is guarantee that the calculations in both of those systems are exactly the same, which turns out that historically hadn't been the case. So essentially, what we're moving towards more and more is a central calculator for fire danger. I bring this up because of some of the things we'll talk about at the very end. But right now, as the raw station come in, they can go into either database for either a historical calculation or a real-time calculation, and then those indices get published for use. What we're working on now is a way of wrapping that calculator so that we can apply the same calculations to gridded historical data and gridded forecasts. That way we only have one single source code for all the NFDRS algorithms, and it's all used anywhere in any system that we need it in a specific way. So the old system was pretty complicated. The new system isn't necessarily any less complicated. It just has a lot less major pieces. So we had separate models for the 1 hour and the 10-hour fuel moisture. So those are fine dead fuels, like really fine sticks, needles that are on the surface. And then the 100-hour and 1,000-hour, which are larger or coarse woody debris. Each one of those had a different model for calculating the dead fuel moistures. The same with the live fuel moisture. There was a dependency on the 1,000-hour for part of the live fuel moisture. There was a way to actually kind of hack those fuel moistures that was added as part of the 1988 system. So the complexity kind of grew as we tried to adapt this thing and make sure it worked in different places rather than trying to address the core issues of the model. So what we did is go in and essentially pull out those modular pieces and plug in better replacements for those modules, specifically for the dead fuel moistures and the live fuel moistures. And then the last piece was something that we learned over time, which is that the fuel models themselves were very, there were a lot of them. Most of them weren't used, and it turns out that they are highly correlated with each other. So the new system is considerably simpler in complexity in terms of the number of submodels that are incorporated. It still has the same weather inputs, except that we went from daily inputs to hourly inputs, specifically to support the Nelson dead fuel moisture model, which we'll talk about in a second. We added a phenology model to replace the live fuel moisture model and link that into the whole system. And then we've also been working on evaluating the indices that come out of NFDRS and creating derived indices like the Severe Fire Danger Index that allows us to look at the day-to-day variations in fire potential, for the potential for extreme fire behavior. But we also were able to, in this new context, start focusing on these applications, on the preparedness and response applications. How do we take fire danger information through this process, get it into a plan, get it used every day so that people are constantly looking at it and using it. So the dead fuel moisture model now, as opposed to the previous model, is a single model that was developed by Ralph Nelson in 2000. After that model was developed and the National Fire Plan came in and started supporting updating our remote automated weather station network, we started putting solar radiation sensors on all those RAW stations. So now almost every station has a solar radiation sensor. And the reason for that was to pave the way for implementing this Nelson dead fuel moisture model. So the model runs on an hourly time scale, but requires solar radiation as a direct input. There's some benefits to it, and that is that the model itself, the previous NFDRS version required a human being for every station across the entire country for every day to go in and hand enter a state of the weather. That state of the weather was just describes the cloud cover, or is it raining in the middle of the day? And the calculator wouldn't actually work unless a person went in, put in the state of the weather for their weather stations for that day, and changed a code in the system so that it would produce an index. So the system was not automated at all, and not automatable. So this also required separate modeling calculations for fine and heavy dead fuels. So the nice thing about the Nelson model is it's scalable and allows us to replace all the old interconnected models and fix a lot of things, but also to remove this human user required input every day to fully automate the dead fuel moisture calculations. So Nelson is a much more suitable model for this application because it runs every hour. So it's constantly tracking what's happened over the last few hours, and even in size classes like 10-hour fuels, there's a built-in lag that says the fuel moisture in the middle of the day is still dependent on what the conditions were overnight and during the early morning hours. In the past, there was one calculation per day at observation time, and observation time was usually 1,300 hours or 1,200 hours local standard time. And that time is not representative of the worst case conditions, but it also meant that if it rained in the morning and it was clear in the afternoon, the system would show it as clear, the fuel moistures would be very high and unreasonable for the fire danger for that day. So being able to plug some of these things in, use a dynamic model like Nelson has really helped. So the way that Nelson works is that it's just a fully physically based model. It deals with the diffusion and capillary transport of water inside the stick, but it allows you to create sticks of different sizes. So through testing and evaluation, and also through just general diameter classes for the size for the time lags that we're looking at, we came up with four stick sizes that had the correct seasonal dynamics and that worked broadly across the country, and using the same model and the same inputs. So essentially, we create 4 sticks. We drive all those 4 sticks with the same 4 hourly weather variables: the hourly temperature, the hourly relative humidity, the solar radiation, and the precipitation. We incorporate an effect of snow cover for those fuels, and then we allow the model to characterize the different behaviors of different size classes of fuel, and it does that quite well. So one of the things that we've added, well, that's always been there, is a snow flag. So the snow flag in this case was carried over from the previous system, but all it does is create a micro environment between the fuel and the snow surface that says it's pretty close to freezing, pretty close to saturated. There's no solar radiation and no precipitation input. So we just set those for days that have snow cover to reflect the seasonal recovery of fuels under snow. So the model itself is a fully physically based model. So it does all the diffusion and capillary water transport along nodes inside a stick. And I'll show you an example of what that means in a second. But it really just means that we can use the weather data to derive a real surface temperature from an energy balance, looking at the net inputs of heat gains and losses. It can account for dew formation, so it's very handy in the south where you get nighttime fuel recovery from just high humidities. It's not just the south, it's actually also in the southwest during periods of the monsoonal recoveries. And as I said before, it's scalable to any size. So one of the big input differences now is that it is hourly, and it does use solar radiation directly for that energy balance. So having stations, the requirements for stations have changed a little bit, not a lot, but having this hourly telemetered weather along with solar radiation is all we need to implement this model, and then get rid of a whole bunch of user inputs. So one of the big things the reasons why we can do this is because it uses a true energy balance for the temperature, the surface temperature of the fuel. Before, the state of the weather that was entered by a human went in to adjust the temperature and relative humidity at the fuel's surface. So through conduction, long wave radiation, and evaporates. So the heat loss and the heat gain in the energy balance, looking at the ways that heat's lost, the ways that the stick heats up, and the resulting balance between that gives us a surface temperature that can eliminate the state of the weather. So the way that it works totally is that the stick gets divided into nodes from the center to the outside surface, and water, vapor, or solid or liquid water is modeled in a transport function that goes between the stick and the outside. So the outside air sets the boundary conditions that either push water in or pull water out. It does have a wetting function, which is the graph down in the left-hand example. That's different because all of the fine fuels before didn't have a rainfall input. They only had the state of the weather, and the only thing the state of the weather could do is set those fuels to either wet or not wet. So in this case, it looks at the rainfall that covers the stick, how much that can help its fuel moisture recover, and it does that hour by hour. So this is just an example of what a 100-hour fuel moisture from Nelson looks like for Troy, North Carolina. You can see this kind of two periods of low. So the springtime, like where the fire season is bimodal. So you have very low conditions in springtime, and then equally almost as low in the fall, and then recovered in the summer. And the dynamics, if you look at an individual year, they move pretty fast for the southern states. So the live fuel moisture model is something that we've continued to evolve a little bit since we rolled this out. The original model was expected to be replaced at the earliest possible convenience by the developer. So I talked to John Deeming about this at length, the original developer for the 78 system, and they had no intentions of keeping that live fuel moisture model in the system for so long, but it stayed in the system for almost 40 years. So what we needed was a way to replace that with a new herbaceous and woody fuel moisture calculation. And we settled on using the growing season index, which is a phenology model that assesses the seasonal variation of vegetation conditions that are influenced by all the things that plants care about to be happy plants. So GSI is a meteorologically based index. It's basically a phenology model that's generalized to work anywhere in the world. It doesn't require any human intervention, but it reflects the seasonal variations and between season variations of live fuel conditions from just daily weather data. So one of the distinctions between these two models that we just talked about The Nelson model uses hourly data. GSI just scales that data up, looking at the mins and maxes for temperature and other inputs per day. The previous NFDRS system had a ton of inputs just to deal with the live fuel moisture calculation. So looking at green up date, curing date, dormant date, freeze date. And then in 1988, when the system wasn't working for the South, Bob Bergen moved to Georgia to implement some changes for the 1988 revision, that by adding things like the season codes and greenness factors, which allow you to decrease the live fuel moisture that's computed from the 78 system. So these are all essentially hacks to try to give the users knobs to turn to get some resemblance of fire danger for their area. And that's really frustrating for everybody. So GSI is calculated daily, has 4 main inputs. It used to have 3, but we'll talk about this last one in just a second. The first input's really simple. It's just a 24-hour minimum temperature. We know that plants don't like to be frozen. So we know that that defining at least a threshold of it has to be above freezing for the growing season to start makes sense. The vapor pressure deficit is basically just a recalculated version of the relative humidity. And to get that, we basically just use the air temperature and relative humidity from the raw station to calculate VPD, either using the 24-hour maximum temperature or the 24-hour average temperature. And that is a selection that's available for users in the system because they have slightly different dynamics at different places. The photo period is a control that's programmed into plants. They're very responsive to the length of the day. There are places in the tropics that synchronize green up with as little as of a change as 15 minutes in the photo period because the temperature and all the other factors don't vary that much. So the plants are genetically coded to respond to photo period. One of the things that we found lately over the last few years is that having a direct precipitation input into GSI is also valuable. So we use GSI actually in a semi-arid region and through a project with a PhD student from Iraq. And we looked at the relationship between GSI and the vegetation dynamics in those semi-arid regions. And when we added the precipitation control, the correlations between the vegetation dynamics and GSI either doubled, tripled, or quadrupled, depending on where you are. So it's a significantly better way of accounting for the water limits on plants. So essentially the way this works is we take those 4 inputs, combine them into the GSI model with the local site parameters. So the site parameters are configurable, both in Fire Family Plus and WEMS. And then we use that GSI time series to derive the live fuel moistures with some simple scaling principles that we'll talk about in a second. So this is just an example of what a woody fuel moisture would look like, in this case for Troy, North Carolina, around the Uwharrie National Forest. And if you, so you can see the gray line basically predicting when actual green up happens on average. So around March or the 1st of March, the middle of March, and then reaching peak greenness by June, staying green, and then tailing off at the end of the year. One of the things that we've found for the southern states especially is that the choice of photo period is very important for defining when things green up and when they transition to dormancy in the fall. And that's something that's sort of a continued exploration for us, so we can find the best way to represent this. But if you think about this curve in terms of defining when fires happen, it's very encouraging, because generally in a bimodal fire season, like a lot of the South has, so spring fires and fall fires, they happen when the plants are leafless or the leaves are falling from the plants. And that's essentially what this is showing, is that period in the spring and that period in the fall and winter during dormancy should be the periods where the fire potential will be the highest. And that's generally the case throughout the South. So what we do with the GSI is we take the GSI as an input. We have a rescaler that allows us to re-stretch the GSI so that the scale always goes from 0 to 1, so that we can just capture the seasonal dynamics, and it makes it less influenced by the parameters that we pick for that particular station. And then we use those to calculate live fuel moisture. So the way that the GSI works right now, we have a lower and upper limit that defines everything below the lower limit means that it's fully constraining plant growth. Everything above the upper limit means that it's happy and it doesn't matter. So GSI is just a multiplicative model of 4 factors. You calculate a ramp or indicator function, multiply those together to get a value per day. And what we do is set some basic defaults for the scaling and for the green up. And then we define the range of herbaceous and woody fuel moistures that we're going to scale over once we're above the green up threshold for GSI. We do have snow flags built in to prevent things from greening up under snow. And so one of the things that we're continuing to work on right now is the ability to locally calibrate GSI against measured woody fuel moistures. So these aren't from the South, but they're just an example that I could grab quickly to show you why we care. So if we calculate the GSI woody fuel moistures using this precip enhanced GSI, so the 4 variable GSI, we pick the right parameters for that and compare the GSI woody fuel moistures to measured woody fuel moistures. The old NFDRS had a correlation of 0.18, and the new calibrated GSI woody fuel moistures have a correlation of 0.87. So almost over a fourfold increase in the ability to predict the seasonal dynamics of live fuels. And we're going to just keep making that better. We're going to repeat this for some of the southern states as well, because as I said before, we really need to dial in a better set of parameters for some of these places. The last thing really is the fuel models. So in the 78 system, there were they wanted to have 4 fuel models. So they tried to get 4 fuel models pushed through. They had a steering committee. The steering committee said 4 is not enough. They said, how about 20? So they landed on having 20 fuel models for this system. But it turns out what they did is take the 4 that they wanted and they modified each of them about 5 times. So what you end up with are 20 fuel models that aren't independent. If you look at the seasonal dynamics of these things, they're almost identical. In the 88 system, they added 20 more. Some of them were the same, some of them were different. So it was, for all intents and purposes, they're treated as 2 separate sets of fuel models, but the outputs of the models themselves are not unique. So when we apply fire danger, we apply it based on a percentile threshold. So it doesn't matter what the absolute value of ERC or BI or spread component or ignition component is. It's just usually, is this value above the 90th percentile for this day? And that becomes a breakpoint for decision making. So the scale of these things has absolutely no bearing on how we apply the system. So to illustrate this, if we look at a station in Jemez, New Mexico, the plot on the left is the BI and the ER on the top, the ERC on the bottom for 2 different fuel models. These are slash fuel models. If you look at those plots, you'd say these things are totally different. If you take those red lines, you move them over to a new axis and let them float over the top of the other plot, what you see is that the seasonal dynamics of those things are exactly the same. In fact, they have a correlation of 1.0 when we correlate the day-to-day variations and we take out the magnitudes. So there was a real problem with that. So we went in and looked at determining which fuel models are similar, which fuel models are truly different, and then try to break those out into new fuel classes. So that's what we did. We ran ERC calculations for all the weather stations, popped it through this cross correlation matrix to look at the ones that are truly unique. And what we landed on was a system that has 5 fuel types. And now those fuel types tie back to a specific fuel model in the Scott and Bergen 40 fire behavior fuel models. To do that, we had to add 1,000-hour fuel, and then we had to add a drought fuel loading, which we carried over from the 88 system. But for the most part, we have the grass GR2 for grass fuel model, GS2 for grass shrubs, which becomes the NFDRS fuel model W, an X fuel model, which is a brush model for both southern rough and chaparral, a Y fuel model for timber litter, and a fuel model for slash. All basically condensing all 20 down to 5 fuel types that are well defined. So so now we have a simple fuel model table that describes 1, 2, 3, 4, 5 for the new fuel models, and this is it. This is the guts of all of the fuel model, the fuel modeling for NFDRS version 4. So what we did is for a quick verification for all of these changes, we went in and computed the old NFDRS for fuel model G across a suite of grasslands and national forests across the country, and we compared those to fuel model Y. But instead of comparing their absolute values, we compared their percentiles. So the percentiles are on the left. The right is actually the relationship between fire activity for those fuel models, and so the index related to fire activity is the AUC of a logistic regression plotted across all of those forests. And what we see is really good agreement between the old system and the new system, which means that we didn't really break anything yet. We're still learning how this applies across the whole country, but so far so good. In the South, we've had some lessons learned that are valuable, and I think probably misunderstood in the past. Some of the old fuel model G, which is basically just a timber fuel model that got universally applied across the country, doesn't work all that well in the South, and it's partly because the dynamics are different. So in a hardwood forest where you have a period of leaflessness and a period of full canopy closure, the microclimate at the surface is completely different under a full canopy versus under a canopy that has that's dropped all its leaves. So those are things that aren't incorporated in this system yet. Those are future improvements that we already have on the docket for next thing. So a lot of the units in the South are using this fuel model X because it reflects that live shrub condition or the live woody condition better. But it still requires some local exploration and calibration to make sure that it's characterizing the seasonal dynamics the way that it should. Specifically, some of the things we learned is that the concept of green up has been skewed over decades of use. So, for example, in the Pocosin in North Carolina, the concept of green up is used to describe when the foliage in the Pocosin is fully hardened after new growth, and that period may take a few weeks to months after the actual green up has already occurred. So what it means is that green up doesn't mean the same everywhere as it meant before. And so we're still working through some of those semantics and trying to get people to really understand. Well, we're really just working together to try to think about how these things fit together. But I think we're going to end up exploring the fuel models for the South in the future, such that we may need to modify some of the fuels specifically that fuel model X to include a longer lag component. It's a very fast moving model, meaning that it can change a lot day to day, as opposed to something like fuel model Y, which is very heavily influenced by the 1,000-hour fuel moisture, and it doesn't vary that much day to day. So we need something in between, something that's a little bit more that's more robust, probably that incorporates the 100-hour fuel moisture a little better, to look at what that might be for version 5. So some of the things we're working on as well are the indices that come out of the system. So we've been working on the severe fire danger index as a forecastable metric that's categorical and easily applied across the country. And we're really trying to figure out ways to take information like this, distill it down, primarily to inform community safety and firefighter safety, and use it for other things. But so we're learning a lot about how we can, about the relationships between fire danger and fire activity. So this is an example of the severe fire danger index calculated for all of the continental United States. So normalized across the whole country using climatology. And under different categories, the distribution of the number of fire pixels that we see and the amount of fire radiative power for these 5 classes that are derived as part of SFDI, the low, moderate, high, very high, and severe. And as we move into the way that we apply fire danger and calibrate it locally, we're doing more to use satellite observations of fire activity from VEERS and MODIS specifically to either augment or replace or supplement our fire occurrence records, because the fire occurrence records only report, the only reliable date in those records is the day the fire started. Very often the date the fire is declared contained, controlled, and out are a little bit sketchy. So we can't use those dates to define some sort of interval for active fire growth. The satellite active fire products are sub-daily, so multiple repeats per day, and we can actually get days of high activity, days of low activity, and start to see how fire danger can transition us from something that we just use to look at the seasonal locations to looking at something that's specifically day-to-day fire growth or fire activity indicators. Another part of the severe fire danger index is it's very closely tied to when entrapments and fatalities have occurred on fires. So we looked at about 40 years worth of firefighter entrapments and fatalities. And what we found is that those days where when we use the energy release component and burning index from the fire danger rating system, 62% of all firefighter fatalities happen on 3% of the fire weather days. Those are 3% of the days that we can know ahead of time and forecast for the next 7 days to keep people safer. To do that, we're building a simple app called Wildfire Safe that allows us to provide fire environment metrics, automate those so that it's constantly sampling for new fires every 5 minutes and delivering it through a user interface that's both mobile and web enabled, that has a mapping interface and then an incident dashboard. So you can check it out at wildfiresafe.fs.usda.gov. Irwin, this Irwin system that allows us to aggregate all the fire reports in the country from all the different CAD systems that are used to report them. It gives us a real-time way of tracking where the fires are and keeping track of which fires are currently active. So we use that in the app to display the locations and the conditions of those fires, to give a dashboard so people can see multiple fires all at once, to show them what the 7-day forecasts are for that fire, what kind of fuels, weather, topography, and values at risk or that fire is exposed to, what the current fire perimeters look like for those fires as they progress. But we're also doing simpler things like building dashboards that just implement fire danger operating plans that say, okay, for this zone in the Bozeman Dispatch Center, for the 4th zone, we have an ERC percentile of 67 today. Those and usually those percentiles are tied to when we go above the 80th percentile, we do this. When we go above the 90th percentile, we do this. But also following the entire process through to provide the severe fire danger index day by day for those groups. Ultimately, we're just not going to stop. We're going to keep trying to explore the things that make fire danger work, the things that make it not work, and we're going to keep trying to evaluate reasons for the behavior that we're seeing. We're going to keep fixing it because we're definitely not going to wait another 40 years to make changes. So with that, I'll stop and take questions.
Matt. So we do have a couple questions, and as folks come up with other ones, please do put those in the QA box. So the first one, Martin is wondering if wind speed is incorporated into the fuel drying piece of the models.
So it turns out that the wind speed is built into the Nelson model, but it's fixed, which is really weird. So one of the things that we can look at, basically the convective cooling that's part of the energy balance, has the ability to both cool and carry away moisture from the stick. It's just not implemented. So as we move forward, it's on the short list to start exploring how much that matters, because it would it really, yeah, it does matter. We know that, and we know that it's built in there. We just have to plug it in. I'll just click along here. The NFDRS, the conifer foliar moisture content isn't embedded yet because NFDRS, for better or for worse, still focuses on the surface fuels. So those surface fuels are everything basically head high or below, except in brush, like chaparral, that's still considered a surface fuel for whatever reason. We're dealing with like old school thought. So what is on the list for version 5 basically is to start doing a very similar thing to what the Canadian system does, which is to give you some indication of fire type. And to get fire type, you have to leverage information about the canopy conditions. That's especially important in the Southeast because the Southeast has seasonal canopies. So the spring and the fall, leafless in the winter, leafless in the spring until green up, and then you have full canopy closure. So so basically we'll couple the surface fire danger conditions with the entire fuel bed, instead of just looking at the surface fuels. So hope I got that one.
Was that in response to Gary's first question?
To Marty's.
Okay, gotcha.
So Gary says, asking if the surface fire, specifically surface fire behavior, still applied to the new current version. So the thing about the outputs of these models, specifically the indices, is that they didn't change at all. So the concept, the one thing that we constantly teach and preach almost is that fire danger indices are not, they don't have dimensions. They're just an index related to some change in the fire environment. So it's super hard to convert things like ERC to BTUs per square foot unless you have a realistic fuel map that indicates the fuel variation across the landscape. The seriousness of the burning conditions is still captured, but it's captured in a relative way instead of an absolute way. And the hauling charts that we have right now are strictly, they're made more for fire behavior. That's talking about, these are the local fuels. This is the way that this fire is going to behave. And that is a completely different application. And so the second question from Gary is, they only address surface fuel models. I think we maybe got to that already, but the one thing that he's mentioning too is the ground fuels. So one of the things that NFDRS, all of these fire danger rating systems do poorly is deal with organic fuels. So basically a lot of the fuels in the Southeast fall into this category, but also a lot of fuels, the important fuels around the world fall into this category. So there are, but so much of that is developed in, is dependent on the local hydrology in a way that's not really easy to incorporate into something that you just monitor from a single weather station. And I do know that we have to do this. We have to have a way of incorporating this. In fact, the future changes for the Canadian system are already looking at addressing some of these things. But until we find a generic way that we can incorporate it into the existing system, I think it's going to be really hard. We have to, until we can move into a fully spatial part of this system that can also deal with things like groundwater transport, because it's going to matter. And so that's about the best I can give for that answer, Gary. But Martin,
I'll also
Jacob
mention just really quick, Matt, on the organic soils point, for those who are in North Carolina, and I know that Gary is aware of this, but the North Carolina Climate Office does have some organic soils monitoring stations, and I think they plan to potentially expand that. So that won't be helpful to everyone, but for some folks that is available.
Yeah, and I'm not in any way discounting the need or the value for it, because I know it's important. And it's just that, when we're, especially with these initial changes, like nobody had touched this system for 40 years for all intents and purposes. So everything has been painful. And the more we add, the harder it got. So we kind of had to pick and choose. As for the snow flags, one of the things that we already have set up is we're using data from National Snow Data Assimilation System, the SNODAS, to provide real-time snow cover maps that we are going to build in to automate the snow flag. So the snow flags will be fully automated from grids in the future. In fact, once we get to a more gridded application nationally, a lot of these things will be much easier than they are right now. So we took away most of the need to manage the day-to-day stations, but the snow flags are the only thing that still require the users to go in and turn them on and turn them off. But it can really be just once per year in some cases.
All right. It looks like we have one more question. It looks like we have time.
So the black box comment is fair right now, because the equations and algorithms have been in flux. But what I'm finishing right now is the technical document for a peer-reviewed technical document, and that will also include a Dockerized container of all the code that allows you to run a command line version of the equations and algorithms with your own data. And we're testing that right now with some colleagues in Sardinia to calculate fuel moistures and fire danger for the Mediterranean Maki. So once we know that that's going to work, then we will be able to just make it. It will be published and it'll be linked in the publication so people know where to get it. It's much easier to have a document that we can point to for how things work, so that people can use that along with trying to plug the new equations into a project. Now, the one thing to keep in mind is that computationally, that structurally they're simpler, but computationally they're harder. So because they went from daily calculations to hourly calculations, and then for every hour we have the 4 sticks in Nelson that in some cases have 130 sub time steps for the diffusion model. So computationally it's a little bit slower, but you get a lot more out of it, and it's a lot more tunable for local conditions.
Thank you. All right. Well, thank you, Matt, and thank you everyone who was joining us today. Just put up one more screen and share a couple quick reminders. So thank you again, everyone, for your time. Dr. Jolly, thank you in particular. Hope everyone has a great day and a great weekend.